So the first thing to say if we're talking about probability is that it seems to come in various sorts. And one of the standard dichotomies that the philosophy literature draws is to distinguish between subjective probabilities and objective probabilities. So subjective probabilities, which sometimes get called personal probabilities, and which sometimes get called credences, are supposed to be something peculiar to the particular agent. They're measures of an agent's degree of confidence in some hypothesis or theory. And so it's perfectly coherent for, let's say, Harvey and I to have different personal probabilities of a given occurrence. Objective probabilities, which sometimes get called chances, are supposed to be something different. They're not supposed to be something about an agent's relation to the world, not something about my beliefs. They're supposed to be something about the world itself in some sense. And let me illustrate that, and also illustrate that it's not a completely unproblematic distinction by giving a few examples. So here we have something that is very much on the subjective probability side. The probability of Labour winning the next election is 2/3. Now, you can quantify these numbers, you can talk about them. If you've got a view about how likely it is Labour will win the next election, then Ladbrokes and John Williams and people will want to talk to you. Betting shops will cash the odds of these things and will pay out according to the results. And insofar as we can understand those numbers at all as more than just the playing out of a social activity, then if I say I think Labour's 2/3 likely to win the next election, I'm expressing some degree of confidence in it happening that somehow expresses the fact that I'm more confident in the proposition than its negation. And indeed goes further than that and quantifies how much more confident I am in the proposition than its negation. But if you were to say the probability of Labour winning the next election is 1/3, it's not obvious that we're disagreeing about some fact. It's not obvious, that is, that there's a determinate, true answer to the question of how likely it is that Labour will win the next election. After all, we know that's only going to happen once. Here's a borderline case. If I say this coin is fair, I seem to be saying something somewhat objective. If I say, if I roll 2 fair dice, the probability of getting 2 6s is 1 in 36, I seem to be saying something objective. Now, it's not completely clear what I could mean and what that objective thing could be, because both of those systems seem to be deterministic. That is, it seems to be that if I knew the starting physics of the coin or of the die, then I could predict with certainty the result of the throw, of the toss or the throw. And in fact, at least in the case of coins, that's not even a hypothetical. There are machines which will flip coins in a way that will look remarkably random, but which will land heads every single time. I'm told you can actually teach yourself to do this. It could be useful in some contexts. And yet, in another sense, it does seem that there's something objective about the claim that the coin, that if I've got fair dice, the probability of them landing double six is 1 in 36. The entire business model of Las Vegas is built around the fact that we seem to be able to say objective, robust things about probabilities of random events like the fall of dice, the playing of cards, the landing of roulette wheels. Here's a even more solid case. It's a little smaller than I intended, sorry. Quantum mechanics itself, and in particular nuclear and particle physics, seems to deliver very specific, very precise, quantified, measurable claims that nonetheless seem to be statements of probability. The probability per minute of a neutron decaying is 0.068. That doesn't seem to be an expression of my opinion. It seems to be saying something about neutrons. If a decaying nucleus of plutonium-240 decays, the probability of that decay being a spontaneous fission event is 5 times 10 to the power of 8, 10 to the power of minus 8. Very unlikely, but actually sufficiently likely relative to what happens with plutonium-239 that we seem to have discovered an objective difference between plutonium-239 and plutonium-240 that makes a difference to what we can do. And it seems that these are not simply expressions of our own uncertainty or curiosity. These are somehow very objective features of pieces of physical reality And indeed, if we know these objective facts about these objective pieces of physical reality, we can make predictions and constructions, we can do technological things, experimental things, we can do some terrible things. That's Nagasaki. The project of building the atomic weapons in the Manhattan Project relies pretty strongly on what seemed to those project workers to be pretty solid objective facts about the uranium and plutonium nuclei that were involved in the work they were using. Okay, so the subjective probabilities are perhaps not so problematic, but the subjective probabilities don't seem to be the things that are turning up in the physics. They don't seem to be, I should say. That can be challenged. It seems, I've tried to make the case, that there is some objective notion of probability, some robust thing that looks factive, that looks like the kind of thing we work with in our science and measure in our science in roughly the same way we measure masses and charges, at least at a very broad level, that seems to be playing an important role in our doing physics, and that seems to be playing an important role in particular in our doing quantum physics, leaving aside entirely the many worlds theory for the moment. But that concept, that objective concept of probability, is mysterious. Let's break that mystery down a bit and see why it's mysterious. We can distinguish two questions to ask about objective probability, which are notoriously very hard to answer. And I'm going to call those the what question and the why question. Now here's the what question. What, if anything, is the categorical basis for probabilities? And when I'm saying categorical in that sense, I'm using that in the sort of metaphysician sense. What are the, if when I talk about that sample of plutonium or that neutron, and I say about that thing that it's just objectively true that its probability of decaying or fissioning in a certain period is such and such a number, then what thing about that neutron makes it true? It's not its mass, it's not its charge, it's not its height or its width. What kind of actual objective things in the world, what kind of physical properties that a system can have, can make it true that its probability of behaving in a certain way is such and such? And then there's a related question, the why question. Suppose we found something which, formally speaking, has the right kind of properties to play the role of probability. Is that enough by itself to make it probability? Well, surely not. The area, if I take a sheet of A4 paper, or sorry, if I take a sheet of paper that's 1 metre square, then areas of subregions of that sheet of paper obey the calculus of probabilities. Formally, mathematically, they have the right features to be probabilities, and yet they are not probabilities. Those things don't seem to be the things we're talking about when we talk about probabilities. So the why question is then, once we've identified something in the objective physical world, which is supposed to be that in virtue of which a probability claim is true, we need to ask, why is that the case? How is it that those physical facts are sufficient to make that thing a probability? That framework probably looks quite abstract. Let me leave it there as a sort of set of guide rails and show you how that works in a bit of detail. So let's start with the what question. Here's a very tempting idea about probability. Probabilities are relative frequencies. So it's tempting to say, if I were to say, for instance, that a given neutron has probability 1/6, or let's say a die has a probability 1/6 of landing 6, what I mean is something like this. If I throw it 6 times, it's going to land 6 once. Well, that's a terrible account, of course. If I were to roll a die 6 times, of course, on average I get a 6 once, but I might get more 6s, I might get fewer 6s. I'd be crazy to suppose that just because I've rolled a die 6 times and I've got a 6 twice, I should thereby conclude that the die is not actually a fair die, that the probability of landing 6 is not 1/6. So the temptation is to say, fine, let's roll the dice many more times than that. Let's roll it not 6 times, but 600 times. And if I roll the die 600 times, I would expect that I'll get a 6 about 100 times. But notice again that word about. What do I want to say about the situation where I get 200 sixes. Do I want to say that's impossible? I don't think so. What I want to say, I think, is that if I roll a die 600 times, then getting 200 sixes is very improbable. And that's a problem. Because the idea of my project here is to understand what probability is. And I want to make it definitional of a die having probability 1/6 of landing 6, that if I roll it 600 times, I'll get about 100 sixes, then I don't have the resources left to say only if I roll a die 600 times, I'll probably get 100 sixes. That won't do as an analysis of probability. If we understand probability independently of frequencies, then of course that gives me the resources to ground such a claim. If I know already what probability is, and I know how probability is connected to frequency, I can understand the claim that a certain set of frequency results is probable. But if I want to understand what probability is, defining it that way is not really going to help. Okay, so I could say, well, let me define probabilities in the infinite long run. Let me say, as I roll the dice more and more times, the fraction of sixes will get closer and closer to 1/6. So if I were to roll the dice 600 billion trillion quadrillion times, I'll get awfully close to 100 million billion quadrillion sixes. Okay, so there's a technical problem with that and a conceptual problem. Or perhaps in a sense, two different conceptual problems. Here's one problem there. If I were to roll the dice, here's what would happen if I were to roll a fair die 100 million billion quadrillion times. It would sort of disintegrate. So when I say that I'm going to roll the dice that many times, I can't be talking about something that's ever supposed to be happening in the physical world. I must be talking about some kind of hypothetical scenario. And it's quite surreal, it's quite bizarre hypothetical scenario. It's a hypothetical scenario where dice are indestructible. And it's tempting to say that's just sort of loose talk, and that actually what we're appealing to is the sort of ideal properties of the dice. But of course, if what we're appealing to is the ideal properties of a dice that has probability 1/6, if that's what we mean by it being an ideal die, we're begging the question. We're failing again to give an analysis of what the probabilities are. So that's one problem with that infinite long run strategy. The other problem is it would be great, suppose we can understand an infinite long run, it would be great to be able to say, well, as a matter of mathematics, then in the long run, probabilities tend to relative frequencies. It would be great, that is, if there were theorems in maths to that effect. Unfortunately, we can't prove that in the long run, relative frequencies converge to probabilities. What we can prove is that in the long run, relative frequencies converge to probabilities probably. And so again, this is great if we already understand probability and we just want to analyze its statistics. But if we want to analyze and understand and learn what probability is from thinking about frequencies, we're going to find it a very difficult task. Okay, but if probabilities aren't frequencies, what can they be? Because the nice thing about frequencies is they do at least seem to be something objective in the world. They're nicely categorical in my previous terminology. Well, what are the alternatives? Here's the main alternative that gets offered as to how we can understand what probability is. Probability's got something to do with symmetries. So one of the things you might have seen in school, if you remember being taught probability in maths, or if you teach probability in maths, is that the reason it's true that the probability of the die landing 1/6 is the 6 ways it could land. That by itself is not a good argument. Here's why not. Take the die, paint 5 of its sides red and 1 of them green, and ask what's the probability that it lands green when you throw it. And according to that reason, the answer is 1 in 2, because there's 2 ways it could land, the green way and the red way. Something went wrong there, didn't it? So you might think, well, really, when you said there was 1 way it could land that was green, really there were 5 ways it could land. But that's not true. There were infinitely many ways it could have landed. It could have landed this way round, this way round, this way round. It could have landed over here, or it could have landed over here. Counting possibilities is not going to get us there in this situation. What's really going on, I think, when we say that there are 6 possibilities, is that there are 6 indistinguishable probabilities, 6 probabilities that should be regarded as somehow equipossible. And I think our grounds for saying that is something like, well, the die is symmetric. I can rotate one face onto another. And that's a symmetry, furthermore, that's respected by the laws of physics. If the die's pips are made of iron, and if the die is in a strong magnetic field, then the probability of it landing 6 is going to be rather a lot higher, or rather a lot lower rather than 1/6. So that what's going on is that the die has a certain symmetry with respect to the physics it's in. Even that's not quite enough, though. I mean, notice that, so just as a warning that something's puzzling here, suppose I take a die, I hold it with the 6 facing up, I hold it a millimetre above the ground, I let go. Doesn't matter how symmetric it is. You can be pretty confident it's going to land 6. And that points to the real problem with this sort of frequency approach. The die lands one way rather than another. Either lands 6 or it lands 1 or it lands 2 or whatever. So the physical situation can't be completely symmetric. Something has to break the symmetry. Because if nothing breaks the symmetry, then it can't be the case that one thing happens rather than another. So in the case I've just described, the symmetry, it's clear the symmetry is actually broken by the initial condition. And it's obvious how that works. If I were to drop the die from a great height, then the dependency of how the die lands on its initial condition is very complicated and very sensitive to the initial condition. And so in that situation, it's going to be very hard for me to predict how it lands, but it's still going to be the case that some feature of the initial conditions can't be completely symmetric because somehow the symmetry has to go away. Marie Curie has a principle, what's come to be called Curie's principle, symmetry in, symmetry out. If I get an asymmetry in my final situation, I must have put it in somehow. Okay, so those are 2 attempts to analyse what probability could be. Here's a third sort of attempt. This is Tim Maudlin in characteristically diffident style. He says, if someone complains that he does not understand the notion of physical probability, then I am tempted to respond with Dr. Johnson, I have found you an argument, I am not obliged to find you an understanding. That is, I cannot deny the possibility of a sort of cognitive blindness that would make someone unable to understand the notion of probability being used here, and I cannot offer a remedy for such blindness. Don't be bashful, Tim. Tell us what you really think. So Maudlin is saying, and it's a perfectly given thing to say, look, effectively you have to have some primitive somewhere. We understand how to use probability. Those who claim they don't understand probability, says Maudlin, are in a minority. We might not be able to analyse it or reduce it to anything else, but explanation's got to stop somewhere. There have to be some primitives in your story. Let probability simply be primitive. Let there be no analysis. Let's answer the what question by saying probability is part of the unanalysable starting furniture of the world. So much for the what question. Let's think of the why question. So the question here is, if you like, what makes something probability? What is probability, and how does probability connect to other non-probabilistic things in the world? And David Papineau has a very nice analysis of this, where he says, really, when you break it down, there are 2 links between probabilistic claims about the world and other claims about the world. There's a link from the world to probabilities, his inferential link. There's a link from probabilities to the world, his decision-theoretic link. And the inferential link basically says the way we work out what the probabilities are is by counting frequencies. So if I want to determine what the probability of the die landing 6 is, the way I do it is I roll the die many, many times. If I've rolled it n times and it's landed 6k times, then tentatively I conclude that the probability of it landing 6 is k over n, or about k over n, and the more times I roll it, the more confident I am of that assertion. So that's the inferential link. Probabilities from frequencies. And the decision-theoretic link is that knowing the probabilities guides my actions. If I'm told that it's more probable it will rain in July than in August, other things being equal, that's a good reason to hold my wedding in August. If I'm told such and such drug has a higher probability of alleviating my back pain than such and such drug, that's a good reason to take the first drug. If I'm told various things about the probabilities of outcomes and I'm considering how to bet, in a slightly more quantitative way, the probabilities are guides to my actions and my betting preferences. And Papineau says, look, these are the ways in which probability connects to the world, and by the way, we don't understand how any notion of probability has those features. Here's a slightly more systematic way of doing what Papineau does. This is due to David Lewis. Lewis helps himself to that earlier notion of subjective probability we talked about earlier. And Lewis says we understand subjective probability basically fine. It's a measure of our confidence of hypotheses. And the way we understand how objective probability figures into our theories is we understand the link between objective probabilities and subjective probabilities. And his link is called the principal principle. Indeed. And roughly speaking, what the principal principle says is, if you know what the objective probability of something is, that had better be your subjective probability as well. In other words, you shouldn't be able to say, says Lewis, well, the objective probability of this die landing 6 is 1/6, but I'm going to bet at 2 to 1 odds that it's not going to land 6. I guess it's the wrong way round, but I'll bet at 2 to 1 odds that it'll land 6. If I say, look, the objective probability of this happening is very low, but I'm really sure it's going to happen, then, says Lewis, you're acting irrationally. And you can sort of turn that round and say that for something to count as being objective probability, it had better be the kind of thing such that if I know what it is, I set my subjective probabilities equal to it. And there's a slightly more subtle statement of it that says something like, the subjective probability I give to a hypothesis, conditional on the objective probability of the hypothesis being P, is also P. And it turns out that if you buy Lewis's principal principle, you can derive Papineau's inferential and decision theoretic links from it. The price for that is you have to accept the concept of subjective probability, which not everyone wants to buy. Right, but how do we answer the why question? Let's look at frequentism. So suppose never mind how, that I really know the frequency unto the end of time with which this die is going to land 6 when I roll it. Okay. And I know that if I roll this die, let's even be more generous. I know that over the next 100 million times this die is rolled, 1/6 of the time it will land 6. Okay, but I wasn't planning to roll it 100 million times. I'm planning to roll it once and call it a day. So if I want to decide, shall I bet on it landing 6 or not, why is it of the faintest interest to me what its long-run frequency pattern is going to be? And a way of making that vivid is, if we're defining our frequencies ad infinitum, well, the long-run frequency of something happening, averaged as the number of repetitions goes to infinity, is completely independent of the first time I throw it, or the first 10 times I throw it, or the first 10 to the power of 74 times I throw it. Any finite initial segment of an infinite sequence has no effect on the average value of something over that sequence. So it's really unclear, even if we had a frequentist understanding of probability to answer the what question, even if we could look at the world and from the frequencies extract some numbers which have the formal properties of probabilities, it's really unclear why those should have anything to do with our betting practice. That is, it's really unclear why the decision theoretic link should be true. And it's equally unclear why the inferential link should be true. It's equally unclear, that is, why, if all I'm after is an infinite long-run average, that I can get at that by saying I'll just sample a finite part of it. Now, there's space to get around that by saying, well, look, okay, there's space to get around it by the standard philosopher's trick of solving a problem by demonstrating that it is equivalent to the problem of induction, which, since we can't solve, is therefore a sort of panacea moves. So you could say, sure, I can't explain why the first million tosses of the die are going to look like the rest of the tosses of the die, but, you know, that's the problem of induction. I kind of have to assume a certain regularity. And that's fair enough. The difficulty, I think, is the sort of regularity I want to describe is one that we know how to handle and how to describe through the language of probability. And that really takes us back to the what question. It's not obvious we've got a story to tell about how to analyse the world in a way that makes sense of that kind of regularity, which abstracts away from that notion of probability. It's even less clear, I think, why we should accept the principle or the inferential decision theoretic link on Magdalen's primitive conception of probability. In fact, Lewis is quite up front about this. He says, is there any way that any Humean magnitude, he roughly means frequencies, could fill the chance role? Is there any way that an unhumean magnitude could? And he kind of means something like like Magdalen's primitive probabilities. What I fear is that the answer is no both times. So the temptation then is to say, well, this concept makes no sense. He goes on to say, yet how can I reject the very idea of chance when I know full well that each tritium atom has a certain chance of decaying at any moment? That's worth saying, if we could make the symmetry line of reasoning work, we might have a rather easier route to understand the answer to the why question. Why should I bet 1/6 on the diagonally landing 6? Well, because somehow if the world has some objective symmetry, it doesn't really make sense for my own preference structure not to respect that symmetry. But we saw that the symmetry route is also running into big problems. So claim. Where do we get to here? Yeah. Both the what and the why question are actually really rather profoundly difficult to answer. We really are in a very difficult position in philosophy of trying to understand what probability is. We have no really solid, agreed upon strategies, and we have profound difficulties with most of the strategies on the table. So profound that many people are willing to actually bite the bullet and accept that it's all just primitive, that there's just no answer to these questions, just a basic brute fact. Others are willing to bite the bullet and say, even despite the apparent way probability operates in our science, nonetheless, there are, and when I say of the tritium atom it has a certain chance of decaying, I'm not really saying anything about the tritium atom. I'm somehow coding my beliefs.